Hello, everybody. How's everybody doing? Very cool. I'm wasting time while I get the slides up. But I do care how you guys are. All right, so like, what's his name? Like John? Whatever. Like John said, I'm Alejandro Caceres / Alex. I'm with a company called Hyperion Gray. This talk is on rootkits and malware on modern rootkits, on modern Linux systems. Sorry, I have been drinking. So the main thing, TLDR of this talk is, if you get absolutely nothing else out of this talk, it's basically that malware exists, first of all. Malware exists for modern Linux kernels. And at the same time, it has a problem in that it's very loud, right? Like if any of you are familiar with, how many of you guys use Linux? Guys, I use that loosely. Cool. So if you run like a PSAUX, you're gonna see all the processes. Bash is really friendly with all that kind of stuff. So if you run a piece of malware that has no ability to hide itself, you're gonna run into serious problems. So the rootkit part of it is the part that's going to let you hide the malware as you're running it. And basically what this talk is going to do is I'm going to run a piece of malware that's custom written. It's a keylogger, spoiler alert. And then I'm going to run a rootkit such that you can no longer see that keylogger. And then some other little things on the side if I have time. So anyway, that's the TLDR of this talk. Let me go ahead and get to the slides. So the malware that I'm going to be talking about, I know we're talking about rootkits, but a rootkit really needs a purpose, right? That was not okay. Malware really needs a purpose, right? Yeah, malware needs a purpose. Rootkits, what the hell am I talking about? A rootkit needs a purpose. So does malware, and so do all of us, like in life. But yeah, so a rootkit needs a purpose, and really that purpose that we're going to use today, there can be any number of purposes for rootkits. Today we're gonna see hiding a file, hiding itself, and just doing evil, right? So like things like connect backs, reverse shells whenever any system calls are being done. And I'll explain exactly what I mean by that. So we're gonna kind of root this presentation in a piece of malware that I call Kernel logins. I'm glad that got a couple laughs, because if it didn't, I was gonna have to explain that there's actually 3 jokes in there. Actually, I'm going to explain it anyway. There's actually 3 jokes in there, right? So one is that it's a keylogger, obviously. One is that keylogging will help you log into something. And the other one is Kenny Loggins, who wrote, Highway to the Danger Zone. So really important part of the presentation there. So Kernel logins is a pretty basic keylogger for Linux, but I'm actually going to get into all of the internals of how this works on a Linux system. So we'll check that out here in just a second. All right. So keylogging, let's look at the anatomy of this. All we're really doing is reading a file. I don't know actually how keylogging works in Windows. But in Linux, it's basically just a file that records every keystroke that you are ever doing anywhere. And we read that file. So let me go ahead and show you that, actually. And it's not, yeah, well, you know what? I'm just going to show you. And I have a little problem here where I cannot mirror my displays. So I'm going to go ahead and put my VM over here, but I can't see shit on my own machine. So I'm just going to have to like look this way and hope that everything works out really, really well. Oh shit, that's like the spoiler. Okay, so how does this malware work, right? So I have this file here. By the way, can everybody see that? Yeah? Okay. All right, very cool. So I have this file here. I have this file here, project here. Anyway. I have this file here called Kini login. So if you see that executable file, the one in green, that's Kini logins. All it's going to do is log keys. So let's just go ahead and run that. All right. It outputs the number 4. I don't remember why. Just trying to be honest with all of you. All right, here we go. Now let's look into kind of a deep dive. Oh, shit, that's not it. Let's just do kind of a deep dive on what the hell is going on here, right? So let me sudo it real quick. Wait, what? Oh, yeah, no, I'm sorry. I don't know how to Linux. Feel free to correct me at any time, by the way. Hey, thank you. Did everybody see that sign? That's very nice. Super sweet. All right, so I have this little file called CarolinaCon.txt, and the first command that I want is right here. And again, this is how a keylogger works on Linux. We're not yet to the rootkit portion of it. All right, so what I'm doing is I'm reading this file over here called /dev/input/bypath/platform blah 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 -kvd, right? So what we're doing is we're looking within the dev input bypath folder directory, actually in Linux if you want to get technical, and looking for anything with -kvd in it, right? -kvd stands for keyboard. And one particular key that I wanted to show you, where the fuck's my mouse? Is the escape key. The reason I wanted to show you logging of the escape key is because the escape key is 1 in this particular code right here. So we see that we have 1 right here, 1 again right there, exactly where my mouse cursor is. We keep having 1s, and then now, extremely confusingly, I'm going to press the number 1 on my keyboard, and the code for the number 1 is 2. I don't know why they did that, but there it is right there. The rest of the stuff that comes out here is kind of boilerplate Linux stuff. So when you're parsing this file, you do kind of have to look for basically the information that you want. And that's really how keylogging works. I'll show you a little bit more regarding that. Oh, don't do that to me. Yeah, no, actually, I'm going to switch back to my slides right now. Apologies for all the delays. All right, so what did we see right there? We saw lots of hex, lots of zeros and stuff, right? Kind of annoying. But here's a diagram of essentially what Kini logins is going to do, right? So really simple diagram right here. Your keyboard is sending shit to *-kvd, as I showed you, right? And then *-kvd is being read by the system for processing, essentially anything that requires keys, which is almost anything, unless you're using your mouse. All right, so that was kind of like a normal view of what Linux does. So in this particular case, we're going to write a program that reads those keyboard events it's going to decode them in that, all that funny hex that was happening. It's actually going to decode them and turn them into something useful. And it's going to store them on the file system in a hidden folder, and it will extract it off to a remote server, which doesn't need to be done. You can always like kind of have persistent access and store it locally, but it's always nice to get remote things just so you can like sit at your computer and not have to worry about it. All right, so a demo of what Keeney Logins is actually doing is coming up right about now. So as I showed you before, Keeney Logins should be running. Right there. Again, outputting the number 4 for an inexplicable reason. And what I wanted to show you with Keeney Logins is, well, actually, first of all, let me show you exactly what it does. And for those of you familiar with Linux, what I'm doing right there, that ... that's actually a perfectly valid name for a directory. It's just a really mean one. So I'm in /etc, right? But I'm making a hidden folder, which is the first dot, and that hidden folder is a ... Is reserved for going back a directory, except in this case, it's just like a normal directory. And I'm doing it in /etc, which is a place where there's a ton of files, right? So unless you're actually looking for this file, you're never going to find it, which is pretty sweet. So let's actually, before I do this, let me copy this command. Does anybody see my mouse? Thank you, guys. Much appreciated. All right. So before we see any of that, let's go ahead and type a message to ourselves. Like, I don't know. This is a message to myself. Whatever. You guys know what I'm getting at. So some people wonder, like, why do like presenters forget how to use computers just all of a sudden, like once they get like up on this stage or whatever? And a big reason is, first of all, we're always like a little nervous, I think. Oh, by the way, this is a message to myself. Shows up right there. There's some repeated characters, and that's just a bug in Keeney Logins, but let's just pretend that never happened, and we'll move on from there. And I'll go back to what I was saying before about why we forget how to use computers. So first of all, that VM, I'm not seeing that here. I have my slides here, my VM there, my keyboard here, which I normally use an external keyboard. So that's kind of why, and sometimes you're using somebody else's computer, which is why like you it looks like you're an idiot. Like it's like, I don't know how to use a computer. But that's cool, because now you guys understand. What is it, Shift F5? Okay. So I already showed you all of that. Yeah, so you might be wondering if it's annoying to have to add all this keystroke codes manually, like that 0001, 0002, 0003. And the answer really is yes. You have to essentially map each one of those to an actual key. And I was going to show you that, but I think I'm going to skip that right now because we're probably running short on time. I don't know. Okay. The guy's like, whatever. I don't give a shit. So that yes, let me show you. No, let me not show you. The fuck? Oh, I went backwards. Demo of Keeney Logins. I already did all of that. All right, so finally we get to the rootkit portion of it. Not much left in the presentation, actually. But kernel mod rootkit, also known as an LKM rootkit. LKM stands for Loadable Kernel Module Rootkit. It's probably the simplest type of rootkit, but it's still extremely effective. It works on the 4.x Linux kernel, which is the most modern one. I should say they work on 4.x Linux kernels, the most modern Linux kernel. So they still work. They're hard to detect. And it's called a rootkit for one really important reason. It assumes that you've already done all of the privilege escalation stuff, and you're just trying to persist access, hide files, and do other really malicious things. So here's like a diagram of exactly what I'm talking about. So this is a normal Linux system, right? So let's start at the top right there where it says process. Process is a user, right? So that's user space that we're working with. Process calls a system call handler, which means that, for example, we want to open a file, right? Or let's use the example of writing a file. So we want to write a file. It calls a system call handler. That system call handler is exposed as a function for a user. Generally you would be writing this in C code because Linux is natively C. So it calls the system call handler. The system call handler looks up where the right system call is on the system call table, which is just a table that holds all system calls, obviously. So it's got stuff like write, open, close, mkdir, all of those things are Linux system calls, right? And in this case, we're doing a write syscall, and then you see at the very right of the diagram, we're doing a write, which is cool. So now you see pretty much the exact same diagram, except we have that loadable kernel module right in between the system call handler and the write syscall. We have this loadable kernel module. So what does that do, right? It replaces the address in the system call table with the location of our own write function. So what we're doing is the system call table is looking for a function, right? Let's say we call the write function. It's looking for where that write function is in memory. And what we're doing is we're overwriting that system call table and saying, no, don't look for this. Don't look for it in this address space. Actually look for it in this other address space. And that other address space is somewhere that we control, and we can do whatever the fuck we want, which is really cool. So this is kind of what it looks like, right? So we replace the address in the system call table. It does the evil write, right? Which is just kind of our new write function. Evil write is executed. We typically will do the evil write and then call the actual write so that it's not detected, right? So we're actually calling the syscall at the very end of whatever malicious thing it is that we're doing. So here's some syscall examples just to give you an idea of what exactly an LKM rootkit can do, right? So we have process control. We can load, execute, end, abort, create process, terminate process, file management, delete file, open, close, read, write, reposition, get/set file attributes. In particular here is where we can fuck with permissions, which is pretty cool. Device management, we can logically attach or detach devices, which is awesome. Release device, read, write, reposition, again, get set device attributes. Information maintenance, so this is where we can really start to do some like anti-forensics stuff, where we can I lost my train of thought. Give me 1 second. My spinach. Right. So what we can do with anti-forensics is we can change timestamps on files, right? So we write a file and then we say, nah, this was created like a year ago. Like, fuck that. You don't need to worry about it. But in reality, you actually do need to worry about it because it's a horrible file. Did I get to communication? No, communication. So you can open TCP connections, open UDP connections, all kinds of stuff. So we can actually exfil traffic very easily, and we can also hide the exfil of that traffic, which is pretty cool. Another kind of class of syscalls is tomfuckery. You can generally just fuck about with the system. Real category. So let's go ahead and see rootkits in action, right? I'm going to show you a rootkit called diamorphine. Is anybody familiar with what diamorphine actually like is? Not the program, but like the word. Heroin. Yeah. Who knows heroin, and how do I get to know you? Oh my God, get me the fuck out of Emacs. I swear to God, I'm gonna, you know what, new terminal. Okay, so we have Kini logins running, right? So if we do psaux grep Kini, we see, yes. So we see a number of processes related to Kini logins. I think I ran it with sudo, which means that you'll see two processes, one of them sudo and one of them not sudo. Is that correct? No. No, I'm actually legit just running two Kini logins processes, which, by the way, is why that message was all fucked up, because it was doubling up on the key logging. Yeah. That's right, my software works. It's just the implementation details are not great. Everybody still good? Everybody following along? Good? Okay, cool. Is this interesting? Anybody? I could just stop. Okay. Actually, I might do that, yeah. You know what? I'm not going to do that. Yeah. No, I appreciate the hint. It keeps me working. Okay, so let's see what we can do with a rootkit. Nope, that's not what I wanted. What did I say? I was going to show you diamorphine / heroin. Which, who was it? Who was it, the new heroin? Yeah, you knew heroin. Cool. All right. So in order to actually use this kernel module, we have to use a command called insmod, which is just insert module. And we're going to do diamorphine.ko. KO stands for kernel something. Anybody know? Anybody? What's that? Kernel operations? I don't know. I actually don't know. I was literally asking if anybody knew, because I have no fucking clue. I apologize. Just for myself. So diamorphine has been loaded, right? If I do lsmod, which is just listing all of the modules, and I do a grep for diamorphine, it shows absolutely nothing, right? So the rootkit has actually already hidden itself. Just by the operation of loading itself, it hides itself automatically. And we're going to actually go to the README for this, which I know is super exciting in a presentation. That's what you want to see, is READMEs. But in this case, it's actually pretty cool. There's a couple things we can do with that I wanted to show you. So files or directories starting with the magic prefix become invisible. That's one thing that I'm going to show you. The other thing is that we can hide and unhide any process by sending it signal 31. So how do we send it signal 31, right? So we do psaux grep Kini logins. And what we're going to do here is we're going to hide the Kini logins process. So that's 22,816. So kill minus 31. Oh, shit. You guys can't see that. So kill minus 31. And we're going to do what? Really? What was it? 22,816? Yeah, 22,816. So we're not actually killing this process. So all the kill does is it sends a signal handler to it, right? So a lot of you might be familiar with kill minus 9, which means kill fucking right now, or just the regular kill command, which I think makes it exit with an exit code of 1. In this case, we're just sending it a code of 31. So let's see if 22,816 exists after we have sent it that signal. All right, so one of our Keeney, oh shit, Jesus, sorry. So one of our Keeney logins processes has been killed. Where's my mouse? Okay. One of our Keeney logins processes has been killed, but we want to hide all of them, right? So let's go ahead and hide the other one. All right, so there we go. Let's see if, bam, there we go. So there's nothing in there that says Keeney logins anymore, right? So anybody looking for Keeney logins with the PSAUX, or actually with anything, this is going down all the way to the base, the core of the operating system. So anything trying to look for Keeney logins can no longer see it. There's rootkit detectors out there. I haven't found them to actually work. I've actually like made a rootkit with the name rootkit, run the rootkit detector, and it just doesn't find it. And it's the most obvious rootkit ever. They don't work that well. And the second thing about it is one of them is like called RK Hunter, Rootkit Hunter. The other thing is that once somebody calls RK Hunter, if you already have root access before all of that, you can just replace RK Hunter with something else, right? So you can just say like RK Hunter processing, and then have a little progress bar that doesn't do jack shit. And then you're done and you say, hey, your system's totally clean. You're good. I love you. And that kind of thing. All right. So back to the presentation for just a minute. I have one slide left. No, actually, I have no slides left. This is great. Okay, so the last thing that I wanted to show you was a rootkit that I wrote that's called, it's also called Keeney logins, which is really confusing, but they're all meant to be part of kind of the same ecosystem. Give me just 1 second. I thought I had this up. Sorry, guys. Well, apparently I'm not connected to the internet, so that is okay. Anyway. Just drag this virtual machine on over. Feel free to talk amongst yourselves while I do this. Where the fuck is my mouse again? There we go. And the last thing that I wanted to show you was on this other machine. Oh my God, this is so awkward. All right, so we have Keeney logins. And what I really wanted to show you in this particular rootkit is one thing is just how simple it is, right? So really. Again, like I said, we forget how to use computers. So one thing is just exactly how simple it is. But the other thing I wanted to show is a couple of really important things, right? So what we're doing is all we're doing is we're reading a file, right? So this /boot/system map, if I can copy this really quick. So what that boot/system map that we're reading within that file is that's where we're actually finding the syscall table, right? So well, like I mentioned, that's where we find the address of it. So you can see the address right here. It's FFFFFF818014000. I think I nailed that, by the way. or that was probably like 19 too many Fs. But what I wanted to show you is this is where we actually get that address, right? So KASLR is on, ASLR is on, all kind of address space layout randomization of all kinds is on, but every time we read it from here, right? So it really doesn't matter that KASLR is on at all. And the other thing I wanted to show you was what we're actually doing to the system calls. Was it up there with the right? Oh yeah. So this new mkdir, right? So this is what we're actually pointing that mkdir system call to. So if you can just take a short look at it, don't worry about all this stuff. All I'm doing is basically this function does This function does absolutely nothing, right? So when I try to make a directory, it should fail. This is all open source, by the way. You can go online, you can go on GitHub, copy this, and it actually shows you how to use, how to make other system calls, how to hijack other system calls as well. And like I said, it's actually not that many lines of code. It's maybe 100, which for C is like fucking amazing. So what are we going to do? We are going to enable this particular rootkit. It's mod rootkit.ko. Did that work? That worked. Okay. So we're going to ls here, and let's go ahead and try to make something. Nothing happened, right? Again, nothing happens. So we've effectively hooked the mkdir system call to make it do absolutely nothing. Obviously, this can be much more malicious than that. We are in kernel space, which means we have full control of the core of the operating system. We can do connect backs. We can do key logging. We can do, I don't know, sky's the limit, honestly. So that's pretty much my presentation. Hope you guys, oh, yes, ma'am. I have a shill in the audience. What's going on? Oh, the pseudo password. Nah, that's okay. That whole thing was basically I'm keylogging on the other one. I'm showing that the keylogger was hidden, but I didn't show you guys that the keylogger was still working after that. So I can do that, but you can also just trust me that it's actually working. I mean, like, this face is a very trustworthy face. So, so any questions about things?
Yes, two questions. One is it possible to check the integrity of the syscall table and see if it's been hooked? And two, are there any legit non-evil processes that might do similar things?
Yeah, so yes and yes. I believe that that's how a lot of kind of rootkit hunter stuff works, is by checking the integrity of the syscall table. I'm not sure why it wouldn't detect my rootkit, but yes, definitely. That's probably one of the leading ways to check not to check to detect a rootkit. And your second question, I think actually also plays into the first question, in that there's a ton of legitimate processes that do rootkit like stuff, where they're hooking the syscall table and doing other things like hiding themselves. Especially in Windows, you see like all that shit that comes pre-installed. There's also rootkits that come pre-installed sometimes. That's not rare. It's been found in the wild. So if you like basically ban everything that does anything that looks rootkit like, you're gonna kind of fuck over your own system, right? So that's what makes it hard to detect. So yeah, it's a great question though. Yes, sir. That's a great question. So the question was if I know about any Linux rootkits or rootkits in general that have kind of famously done something evil. If I'm not mistaken, Asus rootkit. There was an Asus rootkit on Asus laptops, like I mentioned, with their like spyware, that was actually sending data back to Asus without the user knowing, which is bad. So that was definitely a root. I mean, I can't say even technically a rootkit. That was definitely a rootkit, and that it's trying to hide from the user. In terms of something like super malicious, I don't know of any famous cases, unfortunately. I wish I could give you a better one, but yeah. Cool. Any other questions?
Here.
Oh, hey, sorry.
Wouldn't it be just as easy to make the syscall table look like the original syscall table so you couldn't detect any rootkit?
Yeah, so the question is, wouldn't it be easy to make the syscall table look like the original syscall table so that it didn't look like a rootkit? And that's a really good question. The problem is that you do need to edit the syscall table to point to a new address, right?
Using your I would imagine that you need to run a command from user mode to do some sort of operation to get access to the syscall table. So you can modify that operation to return whatever the original syscall table is.
Oh, yeah. Yes, you're absolutely right. And most rootkits will actually do that. They'll edit the syscall table, but then eventually they'll call the actual thing. So like that right syscall, or like let's say the mkdir syscall that I showed, I kind of fucked and didn't work. By the way, there it is, mkdir, be hooked, motherfucker. Can't make MK, I need MK nothing. So what I could have that do is instead of doing absolutely nothing, I could actually have it call the real mkdir syscall, and then the user's none the wiser that something is going on. So yes, that does happen all the time. So good question. Does that answer your question, sort of?
Yeah, sort of.
Sort of? Okay. Sorry. We'll talk later. Oh yeah, we have free shirts. It's this same shirt right here. We got coasters. And that's it. I'm out.